All right, chemistry class, I am going to walk you through some sample problems for chapters 16, 17, and 18. Actually, mostly 16 and 18. Those are where the computations really are. And I'll just mention a few things about chapter 17. So this would be great if you spend time actually using this video to review and study. These problems are going to be very, very similar, maybe even identical. They might going to be very, very similar to the test questions that you will see for these chapters. So please take the time. It'll be worth it for you to spend a little time here and use this video here as a study tool. Pause it, copy it down. What you have to do is make sure that you can do these computations. If you just watch me do them and set these up and don't know how I'm doing it or how to get the answer on your calculator, it's not going to be very beneficial. So pause it and review it. Do the problem, try it on your own, push the buttons on your calculator, what you need to do in order to do well for this one, okay? All right, chapter 16 was all about heat, if you remember, and we're going to use this formula over and over and over again, okay? So remember, Q is heat, M is mass, C is the heat capacity, delta T is the change in temperature. So you may be asked to find the heat given these other three. You may be asked to find the heat capacity given the others. Whatever the case is, you have to feel comfortable using this formula. In this first example here, it says a 3 gram, there's your mass. Sample of iron was heated from 0 to 30. There are your temperatures, initial and final. To find delta T, it is always the final minus the initial. So for us, it's going to be 30 minus 0, which is going to be 30. It absorbed 25.2 joules of energy. This is your Q right here. They're giving you the Q value. And it's asking to find the specific heat of this piece of iron. That's the C. You're trying to find C right there. So I could do several things. I could put in these numbers here now and then solve for C, or I could rearrange this formula so that C is by itself, meaning I could take the heat, divide by the mass and the delta T, and now I could find my specific heat by plugging in my values. The Q is 25.2. And I'm going to make sure I have my units here. Mass is grams, 3.0 grams. And the delta T I found here is 30, and that is in Celsius. So to calculate this, you can do this on your calculator. I don't need to do this for you. You're going to take 25.2 joules, divide by 3, and then take that answer and divide by 30. And you will get a value in joules per gram Celsius. That would be the specific heat of that particular piece of iron. Remember what it's measuring. The specific heat is telling you how many joules of energy are needed to raise the temperature of a gram of that substance 1 degree Celsius. Okay? Number 2, we're using the exact same formula, but this time it looks like we're going to be solving for energy. Q. How much energy does a copper sample absorb as energy in the form of heat if its specific heat capacity is 0.45, so they're giving us this C value. And its mass is 100, they gave us the mass. Sorry, 10, not 100. And it's heated from 10 to 50, so the delta T is going to be 50 minus 10. And that's going to give you 40 degrees Celsius. All right, all you're going to do is plug the values in. You're given a mass of 10 grams. You're given the C, the heat capacity, 0.45. And you're given the change in temperature. Now, if you look at the units, you don't have to look at the units to do the computation. Obviously, you can do that on a calculator. But do you see here that grams will cancel? Celsius are going to cancel. Your answer is going to be in joules. So when you take 10 times 0.45 times 40, you're going to get an answer here in joules. Okay? You can do that. Number 3 says find the specific heat. Now again, this is like number 1. So we're going to use the same formula. and we're trying to find this C value. It's given us mass, energy, and initial temperature and final temperature. What you might want to do is pause this right here, set it up, find a value, and then restart this to compare with me. Okay, I'm not going to actually compute it, but you can compare with my setup. So pause it, try it, and then come back. We are trying to find the specific heat. This time I'm just going to plug in my values and then solve for C. Okay? Oops, I actually am given this Q value. Sorry, I'm giving this as 70. And C I don't know, and my change temperature is 90 minus 30. It's always final minus initial. Okay? So I have here my C value. To solve for that, I divide by 5.0 both sides. And then I'm going to divide by, this is going to give me 60, right? So I'm going to divide by 60 as well. Now this is going to give me my C value that I'm looking for. It's going to be 70 joules divided by 5 grams divided by the 60 degrees Celsius. You do that calculation, 70 divided by 5, and then you take that answer, divide by 60, you will have an answer in joules per gram Celsius. Okay? All right, number 4. Number 4 is just like number 2. We're finding the energy this time. Again, we're finding the Q value now. Okay? And this is absorbed as heat. You're given the heat, the energy that is being absorbed. You have 10 grams. So let's just go ahead and plug it in because this is just finding the Q value. The mass is 10 grams. It's heated from 15 to 35. That's my delta T, 35 minus 15. And the specific heat is given to you, 0.13. Just evaluate this. Take 10 times 0.13 times the difference of 35 and 15, which is going to be 20, obviously. And when you multiply that together, you're going to have your answer in joules. Okay? All right, one more here. Again, you should pause. Why don't you pause this again? See if you can get this problem because it's asking for specific heat. Okay? I'm going to rearrange this formula. Specific heat is equal to the heat over m delta T. And what do they give me? They give me the mass. That's going to go in here. They're giving me the change in temperature there from 0 to 45. So 45 minus 0 is going to give me 45. Went up 45 degrees Celsius. Now the change in temperature can be negative too. And you can get a negative change in temperature, but that means your heat is going to be also negative. It's going to be leaving the substance. It absorbs 82 joules. So when you do this calculation, you take 82 divided by 8, and then take that number and divide by 45. You're going to get an answer, and it is going to be in joules per gram Celsius. Remember, that is what specific heat means. Okay? All right, that is what you need to do as far as computations. Now, there are other concepts that you have to understand for Chapter 16, but for computations, this video is to help you with the computations and the calculations for that particular chapter. Okay? You still need to know what specific heat is, the definition of that. You need to know what the units are for heat, for example. What is temperature? How is temperature defined? So those are other things that you need to know. Okay? Let's go on now. I'm going to just kind of brush over Chapter 17 because Chapter 17 was all about reaction rates, and it was pretty straightforward. If you remember, reaction rates had to deal with, I'll just do this really quickly here. If we talk about a rate, it had to do with the change in concentration over the change in time. Okay, this is concentration here. That's how the rate of the reaction is defined. Change in concentration over change in time. How quickly is something being produced, or how quickly is something being consumed? And then you also have to remember the collision theory is particles have to collide with enough energy, and they have to collide at the right orientation in order for a reaction to occur. And then you have to know those 5 things that you can do in order to alter or speed up or slow down, I suppose, the reaction rate. So the nature of the reactants, surface area, temperature, concentration, and then a catalyst. So you need to look back and make sure you know those. Okay? Let's go on to chapter 18, and again I'm going to focus on mostly the calculations here, the computations. In chapter 18 it was all about equilibrium. You have to know what equilibrium is. It is when the rate in the forward direction is equal to the rate in the reverse direction, and the numbers of products, the concentration of the products and the concentration of the reactants, while they don't have to be the same, they're not going to change very much because the opposite rates are going to be equal. So that's when you reach equilibrium. Okay? What computations or calculations do we have to do for equilibrium? Well, let's look at number 6. This is chapter 18 now. An equilibrium mixture of, and you're given 3 things there, SO2, oxygen, and SO3, gases. So this is sulfur dioxide, oxygen, and sulfur trioxide. Those gases are at a certain temperature, and it's determined to consist of 0.3 moles per liter of the sulfur dioxide, 0.1 moles per liter of the oxygen, and 0.5 moles per liter of the sulfur trioxide. What is the equilibrium constant for the system at this temperature? And they have a balanced equation. You must always have a balanced equation. Okay? Fortunately, they gave it to us. If you remember, the equilibrium constant expression is, it's a ratio of concentration of products over concentration of, reactants. Okay? Remember, it is, so let's take our product here. Our only product is the SO3. So it's a concentration of SO3. And remember, that concentration is then raised to a power equal to the coefficient. So this is going to be squared. And then the reactants are SO2, and it's going to be squared. And then the concentrate times the concentration of O2. And it's going to be just the first power. And then all you do, that's the expression. And if you're given these concentrations at equilibrium, it has to be at equilibrium. We are given the concentrations. 0.3 for the SO2, that's in the denominator. It's going to be 0.3 squared. Oxygen is 0.1. And then the SO3 is 0.5. That is also squared. So all you do on your calculator is you take 0.5 squared, divide by 0.3 squared, and then take that answer and divide by 0.1. And you're going to have a number, and there are no units, but that number is going to be your K constant, your constant. And remember, if that K is greater than 1, what does it mean? Well, this is a ratio. If this number right here is greater than 1, that means this top number is bigger than the bottom number. So that means you have more products than reactants. If this K value is smaller than 1, then that means the bottom number is bigger than the top number, and that means that the reactants are greater than the products. If it's around 1 equal to 1, that means approximately the products and the reactants concentrations are about the same. Okay? So it gives us a quick number, quick glance. You know immediately what side is favored at equilibrium. Do you have more products at equilibrium, or do you have more reactants at equilibrium, or about the same? Okay? Now, the other thing we talked about was Le Chatelier's principle. Remember, you can mess with a reaction or a chemical reaction once it's reached equilibrium, and you can start putting stresses on it. And that means that what you can do is, when you start messing with it, it's going to shift one direction or the other, either forward or reverse, to get back to equilibrium. It's always going to try to relieve the stress that you are applying. So let's look at some examples here. Okay? Now, let's look at this one right here. It says, if the system, and you are given a reaction here, 2 moles of carbon monoxide plus oxygen in a reversible reaction with 2 moles of carbon dioxide. And it says it's at equilibrium, and then more carbon monoxide is added. If you bring in more carbon monoxide here, it is going to try to use up that additional amount that you just added. How does it do that? It kicks in the forward direction. The forward direction is going to use up these reactants and produce more of the products. So what's going to happen? Then the forward shift. You're going to have a forward shift until it gets back to that equilibrium constant, making more products and getting rid of some of that reactant, that CO that you added. Okay? So it's always going to shift away from the added or increased concentration. It's going to shift towards the decreased or removed concentration to try to replace it. Okay? It always shifts to try to undo part of what you're doing to it. Okay? Next, pressure. Let's look at this one. Pressure. Remember, pressure on the gases is going to cause them to try to make it more comfortable and relieve some of that pressure. How does it do that? By producing fewer particles. Now, we have to look here for pressure. We have to compare both sides of the reaction. On this side, you've got a total of 3 moles of particles. Just look at the coefficients. Add up all the coefficients. Over here, you just have one product. You have 2. So which side is going to have fewer total particles? The product side. So if you increase the pressure, it's going to shift to produce fewer particles and you relieve some of that pressure. It is going to have, again, a forward shift. And then it'll go back to equilibrium. Okay? Here, what if the pressure decreases? Well, decreases means they can expand. Now you can have more particles. Go ahead. Go to the side that has more particles. What side is that? Well, let's look. 1 here, 1 there for a total of 2. And here we have a total of 2. So you know what? There's no advantage to either side. So decreasing or even increasing the pressure is not going to shift this one direction or the other. So you're going to have neither. Okay? Now, what about temperature? Temperature, you have to think of temperature like a product or a reactant. And it's going to be given to you that way. So look here. Look at this reaction here. Here we have this reactant plus energy. That number right there is your energy or your heat. And over here we got our products. This energy is like a reactant. It's coming into the reaction in order for it to produce those 2 products. So now it says if the temperature increases, that's like bringing in more on this side. It's like bringing in more of a reactant. This heat is like a reactant. If you add or increase something, it's going to shift away from that to use it up. So how does it use up that heat? It shifts in the forward direction, uses up this added heat to produce those products. So this would have a forward shift. Okay? To use up the added heat that you're bringing in. It already has the heat. It has this heat here. It doesn't want more, so it's going to use it up by kicking in the forward direction. Okay? Temperature. What if this case the temperature increases? All right. Oh, this is exactly the same problem. Okay. Oh, I see. It's asking about K. Well, in this case, what happens is, in this situation, the K value will change when you change temperature. Okay. So what happens here? Remember, K is products over reactants. It's a ratio. Well, if you increase the temperature, you bring in more heat here, and it starts to kick in the forward direction, you're going to make what? More products. So this number is going to go up, and this number is going to go down, even making it larger. It's going to increase. It's going to get bigger. Okay? Only with temperature does the K value change. If you change concentration or pressure, the K value is going to get back. It's going to get back to the original K. But here, you're actually going to have a new K value if you change temperature. Okay? And what this is saying here, this K value is not going to change. It's just going to get back to equilibrium. So let's look and see what the shift is, though. If more CO is added, here's your CO. You bring in more CO, okay? You bring in more CO, it is going to shift in the forward direction. But then it's going to get back to the original K value, okay? It will return. It will get back. to the original K. Okay? The original K value. It's going to produce more of the products and take these back down. Remember, you added CO. You're just going to use some of that up, and so that the ratio is back to where it's supposed to be. Okay? Only, I repeat this, only changing the temperature will change the K value. Okay? You have a new K value, but with pressure and concentration, it is going to get back to the original K value. All right. That's really all I wanted to go over. I hope this was helpful. Oh, I'm sorry. Let me go do a few more here. Okay? Sorry about that. I have a few more to talk about. If the temperature of the equilibrium decreases. Okay, so now look what we have here. We have heat on this side. Here's our heat. Okay? Now heat is over here. If you take away some of this heat, it wants to replace it. How does it replace it? Forward direction. So you can have a forward shift. And it will have a new K value. Okay? Let's see here. If the equilibrium, in the equilibrium system, there you go, which reaction proceeds more rapidly at equilibrium? Now, it's kind of a trick question. At equilibrium, what does that mean? It means the forward direction and the reverse direction are happening at the same rate. So neither of them are happening more rapidly, they're happening at equal rates. Okay? You must know that. That's what equilibrium means. And here we go. What is the chemical equilibrium expression? Just the expression for this particular reaction down here. So we're not trying to find the K value, but just express it. Is this balanced? Let's just check really quickly here. I think so, but we have an extra H here. Let me just see what's going on. Okay, I think this H is not supposed to be there. That H is not supposed to be there. I apologize for that, but it doesn't matter. This is balanced, and look at the coefficients. They're all 1, 1, 1, and 1. Okay? So when you have your exponents, they're all going to be 1 because all the coefficients are 1. But we just have to write the expression. It is products, so the concentration of the hydronium ion times the concentration of the acetate ion, which is just this, over the concentration of the acetic acid times the concentration of the water. Okay? That's your equilibrium constant expression. That's it right there. Okay? And all you need to do, if, not in this problem or not, but if you were given the actual concentration of the equilibrium, you just put those numbers in there, drop them in there, and evaluate that particular expression, and you would have a value that tells you, do you have more products, because the K value would be larger than 1, more products than reactants, K value would be greater than 1, or do you have less products than reactants, the K value would be less than 1, or if there's about the same, the K value would be around 1. Okay? All right, that is all I have. I hope this was helpful. If you've got questions, please ask them. I am always happy to help, and I'd be happy to help you with any of these. Okay? So keep up the great work. Let me know if you need anything, and study well for this one. I think you can do very well on this test. All right.